Alright guys, iPad's been charged, so I'm going to continue the video that was put up. I think everybody who takes an online course like this should actually have to teach a course before they take one of these, just to see the nuances of the little things like the dogs barking, the UPS man showing up, the iPad's losing charge like crazy. So anyway, I'm done complaining. Let's get after it now. Let's go back a little bit to looking at the motivation. We saw in the previous video that we could take the sum of the errors, which is equivalent to taking E transpose times E, and we having a very little simple bit of algebra, we created that the errors are equal to y minus xb. And by taking the transpose of both sides, we get this. Now, if we think about where we go from here, let's kind of get on a sidebar first. Earlier in the video, we saw this. And I put this back up because it's a well-known fact that this matrix is the product of x transpose times x. We should know that this is beta. And it's a well-known fact also that this 2x1 matrix is x transpose times y. Now, I think I've actually proven that, or at least illustrated that for you in a previous video. If not, just sit down and create, for example, x transpose and multiply it by y, and you'll see that you get this. So from this, it's easy to see that if we have x transpose x beta equals x transpose y, that we can multiply the left side times its inverse. And of course this just gives us beta. And another way of calculating beta is to take the product of x transpose x inverse times x transpose times y. Now I want to provide a proof of this. Now you've seen this before, but I'm going to go into more detail. So what I want to do is, at the end of the day, we want to minimize the sum of the errors squared, which we now know are just E transpose times E. And using notation that we've talked about earlier in least squares, I'm just going to call this Q. So guys, I'm going to call Q y minus x b transpose y minus x beta. And I want to expand this. So guys, the first thing I'm going to get, I'll get y transpose y minus x beta transpose times y minus y transpose x beta, plus, I need to come down on the lower line here, so x beta transpose x beta. Okay, now cleaning that up a little bit, what we can see is that we have y transpose y. And the second term, we should know by now that we have beta transpose x transpose. And the next term, we're going to have y transpose x beta. And of course the last term we have beta transpose X transpose X Y, right? No, beta. Well, I don't know why it won't let me write that X there, but it sure won't. So, all right, gang. And this is just a just kind of a note where I came up with this stuff. We probably know, but just in case you've forgotten, this relationship is true, and that's what I use to rewrite a couple of the terms. Now, there's also a fact that if we have a one-by-one matrix, that it is equal to its transpose. So if I examine, for example, Y transpose X beta, then what I will end up with is, so Y transpose is going to be a 1, let's see, Y is n by 1, so this will be a 1 by n matrix. X is going to be an n by 2, and beta is going to be a 2 by 1. So if we think about multiplying these two together, we would get an n by 1, and a 1 by n gives us a 1 by 1 matrix. So again, in a 1 by 1 matrix, we know that the product, or the matrix, is equal to its transpose. So guys, what I can do now is I can use that to, and I want to get rid of all the stuff down here. Again, if you need that, all you gotta do is rewind. It's the beauty of having this stuff in video. So what we can do now is we can say that this is Y transpose Y minus beta transpose X transpose Y. And this is equal to its transpose, which will be reversing the terms and giving everything that doesn't have a transpose, and everything that has a transpose, taking it away. Now this leaves us with with this, and you've seen this in previous videos. Now, if you think about it, in the least squares approach, what we would want to do here is we would want to, yes, hold on now, I've got we're going to want to take the derivative of Q with respect to beta. You know, I'm not going to illustrate it for this term, but I am going to illustrate it for this term. So you probably know what's getting ready to happen here. That's going to be a homework assignment for you to illustrate how we take the derivative of a term in this expression when we have matrices involved. So guys, what I want to do here is I want to examine the term beta transpose X transpose X beta. And you know, I want to look at the sizes. So beta transpose is a 1 by 2. X transpose is a well, X transpose X here is going to be a 2 by 2, and beta, of course, is going to be a 2 by 1. So you can see what I'm going to end up with is just a 1 by 1 in the very end. So let's see how this all works out. Now, gang, you should know that X transpose X is the matrix that we talked about earlier. So letting all this play its way out, we know beta transpose would be, and X transpose X is going to be and of course beta is going to be this. Now, what I want to do first is I want to see what the product of the first two matrices looks like. So what am I expecting? I'm expecting a 1 by 2 matrix. So I'm expecting one row, and I'm expecting 2 entries. Now, when I multiply the first row, the first B0 times the see, I'm going to take the row times the column, so I'm going to get beta 0 in plus beta 1 some x's. And then when I take this term times this column, the linear combination, I get, let's go back here. So I'm going to take, I'm taking this row times this column. So I'm taking, for the first one, I'm taking beta 0 times n, beta 1 times some x. And I'm taking the same row times the second column, doing a linear combination. So I got beta 0, I don't think I said that correctly, but so I get this, okay? So I now need to multiply this times beta 0, beta 1. So again, I'm going to take the row times the column, and I get a linear combination. So I'm going to get n beta 0 squared plus, no, hold on now. Going to get beta 0. I tell you what, I think this is going to be better if I do it this way as a teaching tool. Let's go back here. So I'm going to take beta 0 times this expression plus beta 1 times this expression. Okay, yeah. So what I'm going to get here, I'm going to get n beta 0 squared plus beta 0 beta 1 some x plus beta 1 beta 0 some x plus beta 1 squared some x squared. And we can see that these two terms are identical. And I get this. So guys, this turns out to be equal to beta transpose x transpose x beta. Now, what I want to do next is I want to take the partial of this, actually the derivative of this, with respect to beta. But guys, that's the equivalent of taking the partial of q with respect to beta 0 and the partial of q with respect to beta 1. So guys, ultimately what I need to do here is I need to take the partial of beta transpose x transpose beta x with respect to beta 0 with the partial of beta transpose x transpose beta x with respect to beta 1. Alright, so we need to take some derivatives, and that's going to be fine, right? So, if I take the derivative of the first term of this with respect to beta 0, I'm going to get 2 beta 0 in plus 2 beta 1 sum x plus nothing. Alright, take the partial with respect to beta 1, I get nothing. With this term here, I get 2 beta 0 sum x. And the last term, I get 2 beta 1 sum x squared. Now, clearly we can get rid of the zeros. And what we have from here is we can see that we can easily factor out 2. And what we're left with then is we're left with beta 0 n plus beta 1 sum x and we're left with beta 0 sum x plus beta 1 sum x squared. Now we know that we can rewrite this as n sum x sum x squared times beta 0 beta 1. If you don't believe me, check it out. N times beta 0 plus sum x beta 1 gives me this, and sum x times beta 0 sum x squared beta 1 gives me this. Alright gang, we should know therefore that this is equal to 2 times from earlier. Would we say this can be rewritten as? And then of course we have beta. So the derivative of that term will be equal to 2x transpose x beta. Now again, you know what's going to happen here. So we are in a situation, let's go all the way back, return to way back when. So we were taking the partial of each term, and we were at a point where we had y transpose y minus 2. Let's go back and take a look at that. Make sure I get... Okay, so I've illustrated this right here. So we got negative 2 beta transpose x transpose y. And of course, so when we take the partial of q with respect to beta, we get nothing. For this term right here, I'll go ahead and tell you that you get negative 2 x transpose y. And for this one, we obviously get x transpose x beta. Now we want to set these equal to 0. So we're going to have 2x transpose y equal to x transpose x beta. For obvious reasons, we're going to multiply x transpose x inverse times the left hand side and x transpose x inverse times x transpose x beta. So guys, in the end, we get that we can find beta by taking x transpose x inverse times x transpose y. So guys, this is a well-known fact. This is one of those that's important. Need to tattoo it to the brain, if you will. Now, what I want to do now is I want to get into R and illustrate this calculation for you. Remember, we've already we know what beta 1 and beta 0 are going to be. But if we think of our X matrix, it's going to come from our X values. So, guys, I forget, let me go back and get this stuff. Way back. Good gosh. So 18, 22, 25, 28, and 32. We're not going to get a different answer, but I want to demonstrate how we get these answers, using our raw data, okay, and using this approach. Now, first thing we need to do is we need to 3.5. Okay, is we need to create our X matrix, and I'm just going to call this X MAT. And actually, before I do that, I need to create my ones, because if you remember the design matrix, and that's probably what I should call it, I have to have in my first column, I'll have to have in this case 5 ones. So what I can do here is I can create some ones, as I call it, and I can use what's called repeat integer, and I want to repeat integer 5 times. So if you see, I've got ones that I repeat here. So guys, my design matrix, and I'm just going to call it design, is going to be matrix, and I want C of ones, X. In row will be equal to 5. In column will be equal to 2. And by row is going to be equal to false. Now guys, let's see if I got my design matrix, and it turns out I do. Okay. Now my response vector, which is my Y, will be still, I'm going to do matrix, and I need my Y here. And in row is going to be equal to 5. In column is going to be equal to 1. And by row will be equal to true. Whoa. Okay, So there you can see I have my response matrix. Now guys, again, what do we need for our beta matrix? We need to take the inverse, so I'm going to go solve, the transpose of the design matrix times the design matrix, and then I need to multiply this by the transpose of the design matrix, and then I need to multiply that by the response matrix without an E. So guys, when we get beta, you can see we get exactly the same values that we got using the other matrix approach, and the way we what we got with the straightforward approach. So again, if I wanted to just create my model, the easiest way, I would create a linear model, y tilde x, and you can see that our model, we get the same values for the coefficient estimates. So guys, that's all I got for you. Important video here, but especially showed you something new that I didn't show you in 5500, and that was how to appropriately take the derivative of one of the terms of the expression that we created from the error equal y minus x times beta. So you're going to have some more of this, so just enjoy. Okay. All right, take care.